Okay, so we're looking at numerical methods for finding the area, so i.e. just using estimation rather than actual calculus. So not using antiderivatives, just using our knowledge of area, of rectangles and trapeziums. So there's 3 different ways to find the area under a graph without using calculus. The first one is called the left endpoint estimate. So if you've got a function, x, y, so 1, 2, 3. Okay, so it goes about down like that. So this is the function 6 minus 0.1x squared. So that's that line there. Say, for example, we want to find the distance or the area under the graph between 2 and 6, or our A and our B. So that means that we're looking for the area between those 2 lines, bounded by the curve, the x-axis, and our line above 2 and 6. So left endpoint estimate, what it means is that we make up little columns between the 2 and the 6, and where the top left corner of the column touches the line. So, for example, we go all the way up, touch the line, and then we go all the way across. We'll go to 3 and go up. So you make a column where the top left of the column touches the line. And you can do this for any interval. So we're going to use intervals of 1, so going from 2 to 3, and now we go from 3 to 4. So you make the column touch the line, you go across, and then you go down to 4. Again, make the column touch the line on the left, go across to 5, and down. My graph's hand-drawn, so it's a little wonky, but you get the idea. So make the line touch on the left, and then go down to 6. Right, the smaller you make your intervals, the more accurate your area is going to be. Using this, we're now going to find the area of each of these columns, one by one, and you can add them up, and that would give you a rough estimate for the area under the graph. Do you think doing it this way, you're going to get something slightly over the actual area or slightly under? Why?
Because you can see that there's big ones.
Yeah, because you've got these bits here. So it's going to be slightly over. So it's only an estimate. However, you don't have to do it all by hand, doing like each column, finding the area, adding them all up. You can use a rule. And the rule is ln, L for left endpoint, equals b minus a over n times by f of x0 plus f of x1 plus dot 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 plus f of x n minus 1. Right, the numbers a and b are like 2 and 6 in this example, so those are your domain, I guess you would call it. And n is the number of sections you've divided your graph into. So for this example, we've divided it into 4 columns, so n is 4. So then all you have to do is complete that formula and it'll give you a rough estimate for the area under the line. So L, n is 4 because we divided it into 4 columns. B is 6 minus 2 over n, which is 4. And then you're going to do f of xo. Now, try and squish this in. Xo is your first value. And then it's x1, x2, x3, and x4. So whatever your first value is of the area that you're looking for, that's your x0, then you just go up from there until the end. Okay, so now we're going to do f of x0. Yes, Sheree?
So you know how you said we can divide it into how we want it?
Yep.
If we had divided into 2 to 4 and 4 to 6, would we count that as 1 or 2?
Then 2 would be your x0, 4 would be your x1, and 6 would be your x2. Yeah. Then, of course, n would be 2. Yeah. Okay, so now we need to do f of x0. So we need to take x0, which is 2, and substitute that into the function. So we're actually doing 6 minus 0.1 times 2 squared. Then we need to add f of x1, which is again the function substituting in 3. And we need to keep adding those until we get to f of xn minus 1. So what's n minus 1? 3. So we need to keep going until we get to x3, which is 5. So we need to sub in 4. And then we need to sub in 5. And stop there. So that's what that dot 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 means, is keep adding however many you need until you get to n minus 1.
Wait, mister, why did we stop at 5? Because n minus 1 is 3, isn't it?
Yeah, because we want to go up to x3, which is 5
Okay.
on the graph. Yeah. And then pretty much all you have to do is work that out on the calculator. You can try and do it by hand, but good luck. It'll take you a while. So yeah, I mean, basically, do it on the calculator. You get 18.6 square units. Because square units, because we don't know what the units actually are. Right, the next one is the right endpoint estimate.
I'm guessing that's a bit less.
Yes, it will be.
So you take the difference and then that's the area. What? Is that right?
Take the average, yeah.
Well, here you've got too much, and now we're going to do too little.
Yeah, so right endpoint estimate, it's exactly the same. I'm just going to do it roughly because it takes a while. So this was our same function. So 2 was here, 6 was here, 3, 4, 5. This time you're going to go up and meet each column on the right side. Like that. So before each column met the line on the left side, now they meet it on the right side. So obviously, we're missing like these little bits up here. So this estimate's going to be less.
Well, and also, miss.
Yes?
Because we're estimating, do we have?
Okay, so the formula for this one is Rn, R being right, right endpoint, B minus A over N, F of x1 this time. So before we start with x0, now we start with x1 plus F of x2 up to F of xn. And just like before, this one would be x0, x1, x2, x3, x4. We should write those in. 3, 4, 5. Yeah, so now we start at x1, which is 3, and we go all the way up to x4, which is 6. So n is still 4. We've still got 4 columns. 6 minus 2 over 4. This was the function. So yeah, sub in x1, which is 3. And then keep going until you get to 6. Whoops. Minus 0.1.
And from this one, you start at x1, and the other one you start at x0 from the right side.
Because you're going from the right side. Yeah. So then, you know, blah, 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 do it on a calculator. It takes far too long by hand. We get 15.4 square units, which is going to be slightly less. Keep in mind that the left endpoint estimate is not always more, and the right endpoint is not always less. It depends on which way the function's going, if it's going down, if it's going up. If it goes up, it'll be the opposite way around. Because if your function is, I'll draw it over here, if your function goes up like this, and you're doing the left endpoint estimate, then that one's going to be less, isn't it? And if you did the right, then that one's going to be more. So it depends on which way your function's going. For this example, the right is less.
So when that happens, you start from x1.
No, you just follow the formula. I'm just saying that just that estimate will be less or more depending on which way the function goes. Yeah. Okay, so 15.4 is our right endpoint estimate. Now, of course, we get the left endpoint is a little bit more, the right endpoint is a little bit less. So if we average the two, we might arrive at somewhere much closer to the actual area. So the other one was 18.6. So if we do ln plus rn over 2, we get 18.6 plus 15.4 over 2, which gives us 17. So we can say that the integral between 2 and 6 for the function 6 minus 0.1 x squared is approximately 17 square units. Now, if you do it on the calculator or with anti-differentiation, you'll actually find that the proper area is something like 17.066. So pretty close. Not accurate, but quite close. Yes, there is more. So the last one is the trapezoidal estimate. Basically, we're looking at trapeziums, yeah. Alright, here's our function. Now for the trapezium method, basically what you're going to do is going to go up just like you did before to each one meets the line, but then you're going to join it up each one with a straight line to make a trapezium. Each column meets the line and they're joined with a straight line to make a trapezium. So they look like that.
So it's just a bit off the line.
Yeah, it's just a bit off the line. So this one will be slightly less because the line actually curves over the straight line. So like if you kind of blow it up, it would be like this. Yeah. Okay, now if you wanted to do this by hand, I might fill these in first. So 2, 3, 4, 6. If you wanted to do it by hand and calculate the area of each column and then add them all up, you need to just use the formula for the area of a trapezium. Do you remember what it is? Yeah, so half A plus B times height. Yeah, so you can use that by hand, but there is another formula to go straight to it, which is Tn, obviously T for trapezium, B minus A over 2n, don't forget the 2. I might actually need a new line to do this. It's quite long. No, keep it there. I'm just rewriting it down here.
What's that long?
Yeah, it's pretty long. Okay, so it is f of x0 plus 2 times f of x1 plus 2 times f of x2, go all the way up to 2 times f of xn minus 1 and 1 times f of xn. That's it. That's a long one. Yeah, so basically you start with the first one, you end with the last one, and everything in between gets multiplied by 2. Yeah. So n again is the number of columns. So we've got 4 sections. I'll fill this in as well. So this is x0, x1, 2, 3, and 4. So B is 6, A is 2, 2 times 4. F of x0 is 6 minus 0.1, 2 squared. The next one you multiply by 2. So we're going to sub in 3. We're going to sub in 4. Sub in 5. And then multiply the last one by 2. Squish it in. 6. Got it. One line.
Surely this is going to be on the text. Yes, don't call me Shirley. Shut up, Jono.
Oops. Correct. That should not be multiplied by 2.
Good pick up, Matt.
Good pick up. Didn't do that on the sheet, I don't think. No.
What was it pick up?
I accidentally multiplied the last one by 2. It's not meant to be multiplied by 2.
Do we have to write this all down on our paper?
Yeah.
Clearly, Ben.
You should write it all down. I mean, it's one line. Okay, once again, you just do it on the calculator. Make sure you include the appropriate number of brackets.
How many errors are we going to make?
And you get 17.
Have some hope, Stephen.
So that one, quite accurate. Slightly less, because the real one was 17.067. So slightly less, due to the fact that it is, the trapezium is slightly under the curve. Ever so slightly. So we can say, in conclusion, that the integral between 2 and 6 for our function, oops, missed this from the last one, dx, is approximately 17. So that's what you've got. You got the left endpoint, the right endpoint, and if you take the average of the two, you get quite close. And the trapezoidal estimate gets you also quite close.